First of all, I must thank to my students who encouraged me to come here again for uploading a new chapter, Chemical Kinetics. And the chemical kinetics is a very important chapter and spread over throughout the whole chemistry, and also it is very important but challenging. And I know some persons will always like to take the challenge. Before talking to the chapter of chemical kinetics, I must have to say something about the chemical reaction. In short, chemical reaction, just like a medical process, suppose two or more substances or sometimes one substance, whenever undergoes the chemical reaction, total identity of the substance is changed. Say for example, ammonium cyanate, whenever undergoes the reaction, it will give you the urea, which is very versatile reaction. And this urea is very important as fertilizer and which helps to grow the green revolution. So, chemical reaction, you may call it a magical process. Say one animal, if enters into the reaction box, another different animal enters into the animal box. Whenever they will undergo this magical process, they are coming to a new animal. So one rat and one cat may be mixed up in the reaction vessel to give you one small dog. So this is a magical process. So chemical reaction has actually three aspects. First of all, whether the reactants will undergo the chemical reaction or not. This is the first question. And first question, which called the feasibility of a reaction. Whenever you are adding the two substances under this experimental condition, whether these two substances will react or not. So this is the experiment feasibility or possibility of a reaction. And the answer to this feasibility of a reaction comes in most important basic chapter, thermodynamics. Thermodynamics will predict whether the reaction will occur or not spontaneously. And suppose condition for spontaneity of a reaction is that del G at Tp, if the reaction is carried out at constant temperature pressure, it is equal to the summation of G of the product minus summation of G of the reactants. G means free energy. Free energy, the name implies the meaning of this G implied its name. Free energy means energy free for the substance to undergo the chemical reaction. It is the free energy or ability to undergo the chemical reaction. So, whenever the summation of free energy of the reactants is greater than the summation of free energy of the products, the reaction will occur spontaneously. And you know, at the start of this reaction, there will be more reactants and no products. Most of the reacting components are reactant and product not yet formed. So the free energy, summation of free energy of the reactants is high. Summation of free energy of the product is zero at this initially. As the reaction proceeds, it is also increasing. So whenever this one is greater than this, and the delta GTP is negative, means reaction occurs spontaneously. Reaction will occur spontaneously. Reaction is possible. Reaction is feasible. But as the reaction, and second aspect of the chemical reaction, as the reaction proceeds, reactants are depleted. So summation of free energy of the reactants is also decreasing, and products are forming. So summation of free energy of the products are increasing. This one is decreasing and this one is increasing. So after a certain time of reaction, when the reaction proceeds to a certain stage, both are equal. So at this time, this is equal to 0. Means the reaction attains equilibrium. Reaction stops virtually. If the reaction occurs in both ways, suppose hydrogen gas plus say I2 gas, giving you twice HI. Yes, this is sign of reversibility. It is the sign of reversibility. Means the reaction can go in both the directions. So whenever the both first term and second term becomes equal, reaction virtually stops. Means reaction occurs in both the directions with equal rate, and there is no change of the concentration of the reacting components whenever the reaction attains equilibrium. So, this magical process, chemical reaction is a magical process. It has certain properties. It has also certain properties. Whenever they combine to give you the totally new properties. Another example I can also say, hydrogen gas plus half oxygen gas and sign of reversibility to water vapor. This is also another reactions. Hydrogen having certain property, oxygen also having its own identity. When these two reacts, give you a product which is having a totally new product, new substance with a new identity. Hydrogen, say, burns itself. Oxygen helps to burn, whereas water stops the process of burning. So this is chemical reactions is a magical process. So first question, feasibility. First aspect, physical feasibility. Second aspect, how far a reaction can go. It is also very important, and this is dealt in chemical equilibrium chapter. And suppose here, if you take 1 mole of hydrogen and 1 mole of iodine under a certain experimental conditions at a certain temperature pressure, HI is produced. It is not that the whole of hydrogen and iodine that you have taken in this reaction vessel is completed. Only say 83% hydrogen reacts with iodine, give you this HI, and the rest of this hydrogen remains unreacted. So it is the incompleteness of a chemical reaction. And the third aspect of chemical reaction, which is very much important and which is our interest of discussion, that is how fast a reaction can go. How fast a reaction can go. What will be the time required for the reaction to attain equilibrium? This is a very important chapter, an important aspect of chemical reaction. And whenever we talk, and this is dealt in chemical kinetics. And this lecture is just an introduction only for the starting of this new chapter. And whenever we talk, the time required for the reactants to attain equilibrium or complete the reaction, we must have to discuss the rate of this reaction. The rate of this reaction means how much the concentration of the reactants or products, how much the concentration of the reacting components change per unit time. This is the rate. And rate, rate depends on the time of starting of this reaction. As the reaction goes on, the rate of this reaction is falling. Say if we draw a curve, say this is rate and this is the time. This is 0 time. So at the start of this reaction, the rate is very high. Say here. And as the reaction proceeds, the rate of this reaction falls. The rate of this reaction becomes like this. Most of the reactions will have this criteria except the zero order reaction. Except zero order reaction, in which the rate does not depend on the concentration of the reactants. And and in this chapter, this can be illustrated by an example. So one boy runs 10 kilometer distance. Whenever he starts this process of learning, its speed is highest. As the distance is going on, as the timing is advancing, the speed of this boy is getting lower and low. When this boy reaches the destination, its speed is almost 0. So this is also case in this is also the similar case in chemical kinetics. Whenever I shall deal with, so naturally, as the rate depends on this time, we shall have to discuss the instantaneous rate at a particular time. Say at this time, the rate is this one. This is T1 and this is say R1 rate. This is the time T2 and rate is R2. These are the instantaneous rate. On that particular instant of time, what will be the rate of this reaction? Of course, here in this chapter, we shall not discuss the highly fast reactions. Very fast reactions are excluded from our discussion. Say ionic reactions. If you in a solution of silver chloride, if you add, this is aqueous, if you add silver nitrate, aqueous, and in a 1,000th fraction of a second, the reaction is complete and it gives you the silver chloride precipitate plus sodium nitrate. Sodium nitrate aqueous. So this very first reaction is very difficult to find the rate of this reaction. So this very fast reactions are excluded. And also the very slow reactions. Say rusting of iron in presence of the moisturized air. This is a very, very slow process. This type of very slow reactions we shall not also study or discuss in our chapter. Only the reactions with the moderate rates, say decomposition of hydrogen peroxide, say mutual rotation of sucrose, hydrolysis of sucrose, or the hydrogen bromine reactions. These reactions with moderate rate we shall discuss in our chapter. So we like to express how to express the rate of a reaction. Say A to P. A is the reactant, P the product. A is taken, very simple reaction, unimolecular reactions. Example of this unimolecular reactions I have already told. Ammonium cyanide undergoes the urea. One molecule to one molecule conversion under this experimental conditions. So this how to express this rate of this reaction. Rate of this reaction are equal to, in terms of A is reactant decreasing with this time. So it will be minus the molar concentration of A divided by dt. Differential form. A is decreasing, So concentration, molar concentration, the molar concentration of A, third bracket indicates the molar concentration. So this one is itself negative, here is negative. So the rate is the positive. This is the instantaneous rate, differential form. Within a small interval of time dt, the concentration of this molar concentration of the reactant A changes. So in terms of product, again we call plus d p divided by dt. P is increasing, concentration of P is increasing. So this term is positive, this is a positive. So this one is also. Rate is always positive. Rate is always positive. What will be the unit of rate? Unit of rate generally it is the molar concentration. Molar to numerator is mole, liter inverse, or you can say decimeter minus 3. And in denominator, time means second, so this is the second. One small problem I can also give here. However, you can express this rate in different ways. Molecules per cc per second, molecules per cc per minute, and so on. Say one problem. A rate of a reaction is 1.0 into 10 to the power minus 10 to the power minus 5 mole decimeter inverse 3 second inverse 1. Express the rate in terms of molecules per cc second inverse. Decimeter inverse 3 means per cc. So the answer rate equal to 1.0 into 10 to the power minus 5 mole decimeter inverse 3 second inverse. So whenever I like to convert this mole into molecules, 1 mole of any substance will contain the Avogadro number of molecules. So this will be 1.0 into 10 to the power minus 5, and mole means 6.023 into 10 to the power 23 molecules. And decimeter, 1 decimeter equal to 10 meter. So it is a 10 centimeter minus 3 and second inverse. So it is equal to 6.023 into 10 to the power 3 minus 5, 15 molecules centimeter inverse 3 second inverse. Means per second time per cc of this reacting components, the 6.023 into 10 to the power 15 molecules will react. This is the one short problem, and this problem is set in Baroda University 2003. Now I like to express the equation for a chemical reaction in a more general type. Say nu1 A1 plus nu2 A2 equal to nu3 A3 plus nu4 A4. Nu1, nu2, nu3, nu4 are the stoichiometric coefficients. Means in this proportion, the reactors are converted into product. Say nu1 mole of A1, nu2 mole of A2 reacts to give you nu3 mole of A3 and nu4 mole of A4. A1, A2 are the reactants, A3, A4 are the products, and so this equation we can write like an algebraic equation. This is 0 equal to minus nu1 A1 minus nu2 A2 plus nu3 A3 plus nu4 A4. Or in short, you can write 0 equal to summation of nu I AI. Nu I is negative for the reactants, for reactants, and positive for the for product. Products. Say for one example, twice N2O4 nitrogen pentoxide decomposes to gives 4 NO2 plus oxygen. 5 into 2, 10. 10. So rate, if we write this equation for this reaction in a general type, this will be equal to 0 equal to minus 2 N2O5 plus 4 NO2 plus oxygen. Nu1 equal to minus 2, nu2 equal to plus 4, and nu2 equal to 0, nu3 equal to plus 4, nu4 equal to plus 1. And the rate, whenever we shall try to write down the rate of this reaction in general form, it will be like that. Say Ni means number of moles of the ith component at a given time, at a particular distance of time, equal to Ni naught. This is the number of moles of the ith component at the starting point, plus mu I and xi. Xi is a new term. Xi is the extent of conversion or degree of advancement of a reaction. Xi equal to, whenever xi equal to equal to 0 means at the start of this reaction, and xi equal to 1, it is the starting, and 1 it is finishing when the reaction is complete. Xi is the degree of advancement of this reaction, how far the reaction is advanced. So this nu I varies with time. If it is reactant, then with the time Ni is decreasing. If it is product, then Ni is increasing with the time. This one is fixed. This one is fixed, initial. In case of reactant, it is maximum. In case of product, initially at 0. Xi equal to 0, nu I equal to 0. No product is being formed. And nu I is stoichiometric coefficient of this ith component, and this is j, the degree of advancement. If we differentiate with respect to time, then it will be dni by dt equal to, this is 0, plus nu I fixed, proportionality constant, stoichiometric coefficient, and it is di by dt. It is the rate of conversion of this reaction. So this di by dt equal to 1 by nu I into dni by dt. Or if you divide both this side by V is the total volume of this reaction mixture, then it will be 1 by V dxi by dt equal to 1 by nu I, and this V can be written as dni by V, and it is the dt. And ni by V, this is, rather we can write here, ni by V, it is the molar concentration, number of moles per unit liter of this reaction mixture. So now it becomes this one. So 1 by nu I and d, concentration of AI, molar concentration, divided by dt equal to 1 by v dxi by dt. Usually the volume of this reaction mixture has been kept constant. So this is the rate. This is the rate of this reaction. This is the rate of conversion. One example I can show you. This nitrogen, say a nitrogen pentoxide, decomposes to 4NO2 plus oxygen. So the rate of this reaction, you can write in a general way on the basis of this pattern, is minus 1 by minus, it is 2, half the N2O5 by dt Either you form this way in terms of the nitrogen pentoxide, minus is given as the coefficient of this nitrogen pentoxide is minus 2, dividing by this coefficient. And this one also equal to 1 by 4 the NO2 divided by dt, or equal to the oxygen concentration divided by dt. Either you write in terms of the reactants or in terms of the products, rate is same. Rate is altogether same irrespective of the choice of the reacting components. Now I shall discuss how to find out this rate of a reaction. Rate of a reaction experimental determination of rate of a reaction. A simple example reaction is hydrogen peroxide, giving you water plus oxygen, half oxygen. Nitrogen peroxide decomposes to water and oxygen. This rate of this reaction you can determine experimentally. For that purpose, this is the reaction vessel. You have kept this hydrogen peroxide. This is the reaction vessel kept in a given temperature, and certain catalyst you can also add to expedite this reaction. So what we shall have to do, we have to collect the kinetic data. Kinetic data at different time intervals of this reaction, what will be the concentration of hydrogen peroxide in this reaction vessel? What will be the concentration of this oxygen, either reactants or products? So for that purpose, you will have to take L01 amount, say 10 or 5 milliliter, 5 cc in a pipette out, and here some ice cold water have been taken. Ice cold water means some sort of inert solvent, but it is very cold. Its temperature is very low. Just you take by means of pipette 5 ml reaction mixture to this one. When the reaction mixture is added here, due to dilution and due to lowering of lower temperature, reaction virtually stops. Both the factors, dilution slowed down the reaction, and also the lower temperature also again slowed down the temperature. Both together, actually rate becomes very, very low, almost stops. It is called the freezing this reaction. Reaction is stopped. Now this amount of hydrogen peroxide in this L01 amount, you will have to titrate with a suitable reagent. Say in case of hydrogen peroxide, you can titrate with this standard potassium permanganate solution. Potassium permanganate solution. And you can calculate V1 equal to S1, V1 S1 equal to V2 S2, the concentration of hydrogen peroxide in this case. So you will have to make a chart. Concentration of say A or hydrogen peroxide. First I have to take a table. Here time, here concentration of A, here concentration of P. Say A for A to P reaction. At different time intervals, this type of kinetic data we have to collect. Say at the time t, after 5 minutes, suppose at the time t1, the concentration of A1, concentration of P1, and at the time suppose t2, concentration of A2, concentration of P2, and the time T3, concentration of A3, concentration of P3, and so on. At least 10 to 15 data, kinetic data, we shall have to collect. This is very important. This kinetic data very much helpful whenever we shall study the rate equation, order of a reaction, determining order of reactions, and so on. So now we shall have to take a plot. Here the time, here 0, here the concentration of A in terms of this hydrogen, in terms of the concentration of hydrogen peroxide. So concentration of hydrogen peroxide, initially it is highest maximum and then it is decreasing. So if you like to rate a rate of this decomposition of hydrogen peroxide at a particular instant of time, then suppose here T dash, here the concentration of A dash, and you will have to find out the rate of this reaction when the time is T dash or the concentration of the reactants A dash. We shall draw one tangent touching this point, and suppose this is theta. So gradient of this tangent at this point will give you the rate of this reaction at this time T dash or at the concentration A dash. Say 10 theta will give you minus the concentration of A divided by dt. If you like to, whenever depends on the convenience, whether you can determine the concentration of the reactors at different time intervals or concentration of the products at different time intervals. And in terms of this product, say, or either 10 theta or this will be the O X, here Y, it is Y suppose, and it is X. So either 10 theta or you can write perpendicular Y base. So O Y O X. If you plot this concentration of the product with the time, then it will be like this, starting from 0. At the 0 time, the product is, concentration of the product is 0. So at this time, suppose here T dash, you like to determine the rate of this reaction in terms of the product, then you can draw a tangent touching this point, and the tan theta will give you the concentration of P divided by dt. These are the usual process. Some chemical methods like this one, using a suitable reagent, you can estimate the concentration of the reactants or the products, or some physical methods also there. Suppose here oxygen is coming out from this reaction vessel, you can place one idiometer tube and determine the volume of the oxygen is coming out at different time intervals. Then in terms of this product, you can also find a chart, and from this chart you can draw a graph, and from this graph you find out the rate of this reaction at any instant of time. Sometimes initial rate is very important, as whenever the reaction starts, so many complications does not arise. So in this case, suppose this is the initial time. So here we have to draw one tangent touching this initial point. So this is the, suppose, theta. So tan theta will give you the initial rate of this reaction. Or here, this tangent at this, touching this point, will give you the initial rate of this reaction. Initial rate of this reaction is very vital, as so many complications, say opposing process, conjugative process, reversal process, does not arise. So this is all about this. Many physical process methods are also used, say colorimetry, polarimetry, say pressure, or here the volume at constant pressure. All could be used to estimate the rate of this reaction. So this is all my introductory lecture on chemical kinetics. From the next lectures will contain more details of this chemical kinetics. So again, I thank to the viewers for watching this my video and encouraging me to do more video at this very late age of my life. This is all for the benefit of my students who are my favorite persons in life. Thank you all.